Hello, hello everyone. How is it going? How is it going? Hope it is going good with everyone. And it's a chill Thursday evening. It's almost night. Yeah. And what are we doing today? What are we doing today? So I thought today we'll go over some graph problems and learn some graph algorithms. I have not spent a good amount of time with graph algorithms and all that. And I feel it's quite important to know graphs because it's one of the most fundamental problems that you do solve when you actually, yeah, it's one of the most fundamental problems that you do encounter when you actually solve a real world problem. Social media is a graph. um, Social media is a graph. Your social media is a graph. It's a graph of people that gets connected together. If you look at Uber, it is also one of the graphs, because you have different connected cities, you have different connected points, and whenever you're trying to reach from a point to another point, or whenever you're trying to book a particular, sorry, for Uber or Ola, something like that, when you're trying to book a cab, it's basically that how do you find out who's the nearest cab driver to you, right? Available cab drivers to you. So I'm pretty sure some kind of classic graph algorithms are there. Maybe there are some more optimizations and all to it behind the scene, but yes, okay. Yeah. Okay. So that is also one of the classic graph algorithms, right? And the second thing is, hmm. So the second part of it is that if you're trying to work with Google Maps, you try and find out the shortest path, and the shortest path may be depending on certain parameters where it's real-time data feed, and then depending on time, depending on congestion, things like that. Uh, you can then you can then actually see that a lot of heavy use of graph algorithms for sure. Again, from the classic algorithms like Dijkstra, Bellman-Ford, things like that. Maybe there are more optimizations and higher level things that go into research, into going into understanding how uh, we can optimize this thing. So yeah, but at least, like I mentioned, graph is a very fundamental data structure which is used in a lot of real world use cases, and you know uh, to solve problems. So I'm pretty sure what we are going to do is, like, I should be actually starting to learn a good amount of graph algorithms and be more comfortable. Okay? That's the entire goal. So today is day one. It would be wrong to say I haven't solved graph problems. I have, but I have never gone much deeper into it. So that's the plan for this entire series. And yeah, I'm gonna live stream. If anybody has any questions, do drop on the chat. Say hello on the chat, or if you have some kind of solution when I'm stuck like an idiot, to if you want to help out, awesome. Okay, sure. So for this series, I'm basically, I mean, I can probably go back to um, lead code, but the entire point is that instead of doing blind 75 and things like that, I mean, probably I'll go back to blind 75 again. DSA is pretty boring without actual use cases. So whenever I have to do a little bit of short stream, or whenever I don't have time or don't have big chunks of projects to work on, I would tend to do this kind of streams where I just go over data structures. Where I would just go over data structures. Okay. So the platform that I'm choosing today is AlgoExpert.io. I hope you guys know about it. It became pretty famous after COVID, I guess. I don't know if people are using it, but yeah, it has got a good chunk of problem sets here. And maybe later on, we can go to some other platforms like LeetCode, right? So that is what it is. Okay. Saying that, I want to quickly take a break. Not a break. I just want to break for a few minutes. I'll just get something done and then we'll be back. Yeah. Hello, hello, hello. I am back. Hope I am audible. Okay. Let's get started with um, problems. And in here, if anybody has used this platform, you can actually sort, you can actually group by category. That is what I have done. The colors are a little bit off for dark mode. Does it have a dark mode by default? It doesn't for the home page at least. And how does any of the symbols? Okay, this thing still works with dark mode because it has dark mode. But anyways, okay. So I group by category, and the one that I'm going to tackle is graphs. But inside the famous algorithm says Dijkstra topological sort, Kruskal's algorithm, Prime's algorithm, and if I'm not wrong, oh, this KMP algorithm is for your mm, string pattern matching, or like basically finding a needle in a hay, right? So these kind of algorithms. So maybe I'm gonna work with Prime's algorithm, Prim's algorithm, Kruskal's algorithm, topological Dijkstra. So we have to start think about where we start and these kind of things. But yeah, nonetheless, we have to start somewhere. So let's get started. And what I'm gonna do is I'm gonna probably, just in case, start right from the depth first search algorithms, right? So this looks like a very simple thing. And whenever I'm stuck, I'll try to do this. I'll try to see some of the hints, and I'll ask ChatGPT for more orientations around that. Okay, so that is that. So let's create a project. So I've already created a project, but I don't have anything set up. I hope it's visible. So I'm gonna use Java for it. I've been hopping too many languages. I did Python, this, that, and again. So what I personally now feel is let's stick to one language so you can master it. But you should be a software engineer, so you should be able to solve a problem with any language. But again, just like any other humans, you should have opinions and you should have a little bit of biasing here and there, to be very honest. So for me, I'm more biased towards Java, and I'm going to use Java. Whatever. Yeah. Cool. It is what it is. So let's actually set it up. Create an init. So I like to set it up as I need your basic stuff. project name is AlgoExpert is fine, Kotlin is fine. No, yeah, okay. So let's quickly start up the project. So we have AlgoExpert here. This is this open as project. Now, one thing, as I remember correctly, it supports Java 21, if I'm not wrong. So maybe, like I said, I solved a couple of problems. Wait. Oh, okay. This is still like remove stuff. And that is fine. And if I remove the dark mode, I think it becomes a little bit better. Yeah. So I'm sorry for flashbanging on this end, but yeah, just a little bit better here. Okay. Sorry for that if you heard that. My cat is again screaming at the top of his voice, but yeah. Okay. So we're gonna do the depth first search algorithm first, before that we need to set it up, right? So wait a second. Why do you have? Okay, so it has Kotlin because of the Kotlin DSA and stuff like that. So in here, plugins Java, then you have a group. Whenever it comes to this thing, seems like I cannot type. So there is a different, like I mentioned, what I do want to do is system out println. If I'm not wrong, Java standard JDK, find the Java version. I think it was Java. Find Java version using okay. Can I just read Java? Oh. So if I'm not wrong, what you can do is system dot get system Java docs. Okay. Environment get in. Okay, so you can do this. So in here, if I say get in, Java so it uses OpenJDK 21. It uses OpenJDK 21. Now, so we also have to use OpenJDK 21 because some of the syntax in 24 will not be supported in 21. So we have to use 21. Okay. So as far as I know, I can simply just go ahead and compile this. I mean, import this stuff and it works fine. But I do have to set the project this thing. And I like how it's done here. So if I go here and if I say explore, so yeah, this looks a little bit better. And we can simply say this thing. So we can go, okay, what are you talking about? Let's see, maybe the Gradle itself is not supported. So let's do 24. I think the Gradle version is not supported with 21. Oh, we cannot find something of 21, but I thought I have it. Project structure. I don't have 21. I don't have 21, it seems. Okay. So SDK. Let's first update this guy. JK. What the heck is JK? Anyway, SDK install Java 21 open or open 21. What do you call it? SDK list Java. Yeah. So it is 2102 open. 2102. Okay. Meanwhile, how's it going, everybody? How is it going, everybody? Default shower 21? No. We have a little bit of frame drops here and there, but I guess it's okay. So that just crossed, but I guess that's fine, right? Okay, so no. Let's quickly. Oh, I also have this thing enabled for some reason, but okay. So in here, let's say add JD from disk. So in here, how do I go about now? Okay. Dot SDK man and the dates Java. Cool. 2102. OpenJDK specifically. Fly. Okay. Now can I do the import? Okay, it's still okay. So we'll go with 21 itself, so we don't have to, think about language features and all of that. So we can go to project. It's 21, 21, 21, 21. So you can have pattern matching for switch and record patterns. Okay, so I still need to learn a little bit more about how the pattern matching for switch works, but that's fine for now. I guess we are good. Okay, so now let's try and create a directory, and from play dot graphs. Let's just say graphs. Okay, cool. I think we can finally start off with our first problem, which is hmm, you're given a node class that has a name and an array of optional children nodes. When put together, node forms an acyclic tree-like structure. So it's an acyclic thing, which means there's no cycle. So implement the def first search method on the node, which takes an empty array. So this part is very important. For some reason, I cannot copy in here, so they have disabled the copy stuff. I mean, I cannot select and copy, so that is fine, I suppose. So yeah, I don't have any screen markers or anything like that, so I guess you have to just, go ahead with this. Okay, so you're given a node class that has a name. Okay, so the name is a string. Okay, and an array of optional children, but it's not null. It's already, initialized. Mm-hmm. Okay, and when put together, the nodes form an acyclic tree-like structure. Okay, so this is not even a graph because it's acyclic. It kind of becomes a tree, right? Because I mean, all trees are graphs, but all graphs are not trees, right? So implement the depth first search method on the node, which takes in an empty array, traverses the tree using the depth first search approach. So even though it looks kind of like a root, and I'm pretty sure it would be given the root, you do not have to, yeah, okay. So this is a better thing. It's actually given a list of arrays and not um, like just a single node. You can also start from a single node, but it doesn't quite say that you have to start from a single node, right? Okay, which takes in an empty array, traverses the tree using the depth first search approach, specifically managing the tree from left to right, navigating the tree from left to right. Stores all of the node names in the input array. Wait a second. Acha, 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 acha. So it's an in, like, this is a method bind to the node. So this array is just basically a reference pass. Okay. Mm-hmm. And returns if you're unfamiliar, blah blah blah, and all of that. So in this particular case, how it would be a. So can I at least copy? I cannot copy this guy. So so let's just do this. A B E F I J. C G G K H. So now if we start reversing from here, so let's say any node is given, and let's just assume for the sake of the conversation, node A is given. So we start from node A. So if we start from node A, if we start from node A, start from the node A, basically what happens is that it's a depth first search. So if I start from B, I have to go to B. So will it give me a starting point, or what exactly it is expecting from me? No, it's not giving me a starting point, but the sample input output, it's basically very clear that you start from A, but you could have started from any other thing that possibly, honestly, right? Could have started from any other place. Because again, it's graph, and ideally speaking, you always start from the root node, because it's a tree, but yeah, whatever. Solving a problem, so you have B, so you would go back here, and then you still have something else to go down, so you would go down here first. So you would go down to E first. Okay. And once you go down to E, you do not have anything else, so you come back up and you have another option to go down, which is F. So you go down to F. So once you go down to F, you go down to I. Then you go down to J. Then you go back up the tree, and you reach E again. So you go down to C. Then you go down D, G, A, H. Let's see if we got that right. So it is A, B, E, F, A, B, E, F, I, J, C, D, G, K, H. Yeah. I, J, C, D, G, K, H. Yeah. That is basically how we're gonna do, right? So that's basically how we're gonna be doing this. Okay, cool. So in here, so how can we do this, right? I actually stopped it, but how can we do this? So this seems like a more a DFS is more like trying to go down one by one, and then you come back up because you went down to A, from A to B, from B you went down to E again. So E, if you do not have any more path to explore, you come back up. Once you come back up, you have to explore any other path which is not visited as a key, right? So one of the things we can do is use a stack. Well, we can simply use a recursion because of the fact that it automatically by default manages stack frame, right? So recursion is basically calling a function again and again. So you have the stack frame for the function, which has all the details of the context for your function. So whenever you call recursion or you call the same function, it's basically putting a stack frame on top of it for the other function call, right? So that is usually how it works. So by default, it's basically a stack. So what we can do is we can write a recursive function to go down. So first thing first, we have to do this as a pre-order traversal, if I say so, because when I'm here, before I go down, I need to capture this name. Once I reach the end, I cannot capture the name E, and then I go back up, right? So it's not in that way. So it's a pre-order stuff where, uh, is it pre-order? It's pre-order, right? Yeah, it's pre-order because once I'm at a particular node, I process it, or basically here, try and figure out what the name of that node is. And after that, I try and go down to the children. Yeah, so that's basically it. And yeah, I think we can be doing in that way. So let's try to write the structure of the function. So you have, so here it's a little bit different because you have a class node on top of which you have a function. So you have some kind of self thing here. And then you have an array, which is basically a list of strings. And you're not expected to return anything. You're basically expected that it will automatically take care of things, right? It automatically take care of things. So in here, what I'm going to do is, one thing I noticed is that children can never be null. because you explicitly only pre-initialize it right in your um, initializers, right? You already initialize it, which means that it cannot be null. So this is good as, initializing the constructor, so you do not have to worry about it, that it anytime can be null or something. So the way that you figure out that there is no children is basically the size. So what we have to do is traverse the children, not the children, let's call it neighbors, because of the fact that this is like a graph, right? So what you have to do is self dot children for child in this thing. Again, I'm writing more specific to Python syntax, but it's just easy to understand, that's all. That is very true, except the white space and stuff. So for child in self.children, what you have to do is you have to call child dot. So one more thing I would like to check is if the node is null or not. Okay. Because again, I can simply do child dot function call, and I pass in sorry, I pass in the array itself. But in here, your child can be null, right? Your child can be null. So if child is not, so this little check, I would say, is making the algorithm a little bit more production grade, because you have certain null checks, right? You have certain null checks. Okay, so you have this, and that's basically it. But as I mentioned, you have to first, capture the array.pend self.name or something like that, whatever the value or whatever it is. All right. So yeah, that is basically gonna be your depth first search algorithm, right? Yeah, let's go to a quick depth first search. So here is the algorithm. I'll have to do that. Okay. So what do you do for this dot children child? If child not equal to null, you can simply say child dot depth first search, and you pass it there. But it's array possible, and in here array dot well, it's add in here. So this dot, and that is basically it. And you also return the array. Well, I thought you don't return the array, so you technically don't have to return the array. I don't know why we return the array, but technically you don't have to return the array. So that should be it. Let's copy paste this code. They are using a different kind of tablet, but okay. So it passes. Let me submit and see what happens. Cool. Yeah. Okay. So yeah, this is done. What does my title say? What does my title say? Surviving DSA. I survived. I survived the first problem. Awesome. Survived the first problem. Okay. Let's go for the next one. Why did I close it? Like, I was too. Close it. Okay. So if I go to the second one, where's graphs? Okay, let's open it like this. Sorry. Okay. Now we are back to single cycle check. Okay. So you're given an array of integers where each integer represents a jump of its value in the array. Okay. For instance, the integer 2 represents a jump of 2 indices forward in the array, and integer -1 represents a jump of 3 indices backward in the array. Okay. If the jumps spill past the array bound, it wraps around to the other side. For instance, a jump of -1 at index 0 brings us to the last index. Okay, so it's basically like a circular index, right? Similarly, a jump of 1 at the last place brings you back to 0. Write a function that returns a boolean representing whether the jump in the array form a single cycle. A single cycle occurs if starting at any index in the array and following the jump, every element in the array is visited exactly once before landing on the starting index again. Okay. 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 It doesn't have constraints. That's one thing that we have to take into account. So it doesn't have constraints, right? This platform doesn't have constraints, but it's okay. So let's go over the problem again. So you're given an array of integers where each integer represents a jump of its value in the array. For instance, the integer 2 represents a jump of 2 indices forward. -3 is basically on the left-hand side, on the other side. So if it spills, it wraps. Just a second. Okay. Now, yeah. So if a jump spills, blah, 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 I write a function that returns a boolean representing whether the jumps in the array forms a single cycle. A single cycle occurs if starting at any index in the array and following the jumps, every element in the array is visited exactly once before landing back on the starting index. Okay. But the question here is that you can start at any index, and if you start at any index, it still doesn't matter as long as you land back on the same index. But you have to make sure that you visited every single node at least once. At least once or once is exactly once. My bad. It's exactly once. Okay. So the point here is that I can start off at any index, right? So if I start off at let's take a different color. 0, 1, 2, 3, 4, 5. Right. So if I take 5, the question here is, okay, let's just assume we start from 0, right? So we start from 0, so I can go 2 steps to the right. So this is here where I land. I need a marker to say that I visited a certain node. Let's consider these things as a node, right? So if I say that particular thing, I can say that, yeah, okay. So from 1, you go again here. Then you go back -4 steps. So on the left-hand side, 1, 2, 3, 4. So you come back here. So you visited this also, okay? So you visited this also. And then when you do, from here, you go back again 2 steps. So you go back again here. So 3 is good. Then from here, you go 3 steps forward. This is good. And from this, you have -4. So this is 1, 2, 3, 4. This is exactly where we started. This is exactly where we started. Okay. So, take into consideration that one of the things that we can always do is try to figure out what nodes you have visited. If you want to figure that out, you cannot use plus or minus because you have these things in your value itself, right? So I feel you need to have another kind of let's say Boolean array. So everything is false at the start because you never actually visited that index, right? Visited that index. So the question here is, how do I choose a starting point? How do I choose a starting point? Choosing a starting point, in my opinion, can be sequential. So I try to go from 0 and traverse the entire graph. And on a good day, if I start from 0 and I land back at 0, taking all the constraints into account, and I say that, oh, it's working good, it gives me an O of n solution saying, oh, we actually are good. But on a bad day, if I have to check every single index, then what happens is that if I go over every single index, it kind of becomes an O of n squared solution because you might come here and then figure out that if it fails or not, right? So that is what I feel it is. So it becomes kind of O of n squared. Though it's not given the constraints are not given. So I don't know if you can actually go to O of n squared solution, right? So we'll consider that we can do O of n solution. Maybe for now. One of the hypotheses that I'm having right now is because it's always going to jump to and fro, and it's going to create a graph in a way where if you start from a single node, you come back to a single node, the constant is going to be the same for all the nodes. So if you create the graph of where you're jumping from, if you can travel through the entire graph, visiting every node once and then coming back to the starting node, if you can do that for one node, you can do it for all other nodes, is what my hypothesis is. It's a hypothesis, it's just an intuition actually. I have no backing thought to say why it may be true or is true. So yeah. What is one more thing that we can try and work on? I feel another thing that we can try on is actually build up the graph in memory. Okay, actually build up the graph in memory. And if you build up the graph in memory, we can say that if this particular graph doesn't have any cycles, right? That is what we can do. That is what we can do. Anyways, okay. It's almost 39 minutes with just one problem. How sad it is. So how do you do this problem? Let's quickly look at the optimal space-time complexity. The space-time complexity is O of n, and space is O of 1. I have a hypothesis that I have an intuition whatever I said first is correct. So I can start at any single node in here. Okay, I can start at any single node in here and do this. The second thing is what we have to do. So if I'm here, so length is 1, 2, 3, 6. The length is 6. So if I'm at this index, which is 5, 5 plus 2 is 7, mod 6 is 1. So I can easily figure out where I land. But does Java do a proper negative mod? Is the question, right? Is the question. Because when I'm here at index 3, I go -4, which means -1. So -1 mod 6 should be equal to 5 and not -1. So let's see how Java works. Otherwise, we have to write a function, right? So how do you do? So let's just say public int mod. So you take A, you take B. And public int mod int A int B. Okay. So return A mod B. Okay, cool. So I can call 7 and 6. So this should be 1. But what if I call -1 and 6? It gives -1. So that is not the correct thing that we are doing. That's not the correct thing, right? So instead of doing so much of stuff, I feel we can do a little bit better. No, that's fine. We can probably go ahead. Okay. So in here, one of the things we can do is, we can do a proper mod and shift the thing by whatever you're dividing by, right? So if you do that, so now -1, 6 will give you back 5 because you went all wrong. So -1 lands you on 5. So this is correct. But the problem here is now this is messed up. So what you have to do is you have to remod it back again. So you have to so Java doesn't do a proper mod. So but yeah, mod B again. So you shift it, you offset the negative by that number of times, and then you you do that. Okay, so now if I say this, it's 1, and mod -1 and 6 should be this. If you give -2, it should be 4. So this is how it's gonna work. Okay, and you can increment. So you just keep on incrementing stuff. So that's how it's usually gonna go. So you have a proper mod, right? So this is a proper mod function where you wrap around even for negative numbers. This is very useful function when you're doing game of life stuff like that, when you want to wrap around. Anyways, so yeah, I'm gonna do that. So single cycle check. Single cycle check, right? So where is the infusion? We start at any index. Maybe we start at 0, but we can actually randomize it. But we'll start at 0. Since I don't have a constant of how many characters it can be, I'm just going to take an array. But the problem here is that they are looking at O of 1 space, which means I cannot take. What should I be taking? Just once. Okay, we are back. Yeah, so we are back. So start index is this, and once you have the start index, you can say that oh, what was I thinking about? Sorry, I got distracted for a bit for work. Yeah. So what I was talking about here is that so we need a proper mod function. So private static int prop. Let's call it mod. So int x, int y, and return x mod y. This can probably be done in a better way, but this is how I've seen, and this works. So maybe it can be done in a more efficient way with bit stuff and all that. But yeah, just works for me. Anyways, so now I'm not good with bits, but I'm pretty sure I'm going to do some streams where I start learning bits and more number theory stuff. I was pretty good with maths, and I'm not good with maths anymore. But let's see. Okay, what is happening? Okay, never mind. Never mind. So let's see. I hope I'm not dropping frames. I still dropped almost 600 frames, but okay. So now, what I'm going to do is, I'm sorry, int current index equals start index. Not start index. Only thing is, the only thing is, how do I make sure that the array itself is? So one of the things I can do, one of the things I can do is, question is, what if I put a 0? Does it give you a false value? Like, because yeah, you cannot jump to something. Okay, so it gives a false value, right? So that should be fine. And so what I can do is current index is mod start index and array dot length. So this is your current index. while current index not equal to start index, you keep going over the array. And what you are gonna do is, well, start index plus array of start index, right? And in here, what you're gonna do, visited, we can say is visit is 1 because you already started visiting. So what do you do? Int next index, well, I didn't do start index with 0. So int index next index is update the original. Next index is basically a mod of current index plus array of current index and length. Okay. So you try to get the next one. First thing, if array of current index is 0, simply false. Now array of next index, I can mark it as 0, so 0 marks visited, and current index would become the next index. That's basically it. And I can simply increment this thing in here. Now return visited. One thing, what if this is 0? What is the answer here? Your expected true. If you're 1, your expected true. What if it's 0 and 2? 0 and 1. I think you should still expect true because you can start expects false. Boy, why? Oh, because from that node you cannot go to any other node, right? So yeah, you cannot go back to the starting node one more time. That's fine. Okay, so I think we are going in the correct direction. If length is 1, can you have length 0, by the way? And what are you expecting if the length is 0? Okay, cool. So if this is this, return true. And I think that should be it. That should be it. I probably should write down some notes for my future self. Okay, that is fine, but we want to get back to the original array. Okay. The moment of truth is this. Expected output is true, your output is false. Because the first time you're on start index, let me just, I think something may be wrong here, or I'm just completely off. System out print ln this thing. Okay. Start index is 0. You say this thing in here, and you just do that. So current index is not 0. System.out.printf. Index is this, value is this. So even with Java, I think you can do a platform agnostic new line. Yeah, whatever. Who uses Windows as a platform, right? So then you have array of index. I messed up with a very specific something in here, but I don't know. So index is 2. Why is this value 0 is my question. So the first index is 2, which is correct. So from here you go to 2. From here you would just go back here. Cool. You did that correct. So you went back to 3. But the value here is 0. Why? Because it's current index, buddy. Cool. Okay. So let's do this. And let's do this. Let's run this code in here. This is correct. If I submit the code, what happens? Okay, cool. I'll just say it in here, I guess. Yeah. So I'm gonna ask ChatGPT. You are my teaching guide helper. I don't know. I am solving DSA problems. I'm gonna give you the code, and you going to give me back 1, 2 liner revision notes as comments, so I can use those as notes when I revisit. You understand? Do not gap, just notes. It's very important to tell it not to yap, right? Got it. Short version. I think it got a little offended, but that's fine. So, cool. Can you give me the notes for this? Dude, just give me the notes. Just give me the notes in English words, not the entire code. I don't need multiple comments, just the revision notes for a notepad thing. Let's see. I don't know what it's called, like, yeah. But anyways, how's it going with everybody? How's it going with everybody? DSA visit node, then recursively visit all these things, pre-order traversal, add child creates a link and returns a parent. Cool. So we have our revision nodes. It gave it correctly. Single cycle jump to array indices, mark visited, and ensure you return to start after exactly 8 steps. So the only reason why I mutated the original array is because the requirement is O of 1. Otherwise, technically speaking, I would like to store the values in a different thing. In order to check blah blah blah, assume that if you start and jump through, what are the simplest condition? What I want to know first, what I want to know is how do you mark? Could you keep a counter, jump through elements in the array, and stop once you have jumped through as many elements as contained in the array? But once you come to the same element, you just cannot do an addition. You need to have a marker saying, hey, did I visit this element or not? Visited. Okay. Where ends the length must be the first element is visited. The element at index 0. I don't know. Why is it saying O of 1? But we did O of 1. Cool. Okay, so we're done with the map. Breadth first search. This is also another very simple problem. This is also another very simple problem, just like the first. In here, we can use a queue. And the reason why we use a queue is because you take A, you have B, C, D, so you would first process B, then you would process C, then you would process D. You would go back to the first child that you processed, and you would process its children. You would go back to the child of C, and your child C, and then it process its children out of that. So in that particular case, it should be A, B, C, D, A, B, C, D. It should be basically in Lex order, A, B, C, D, E, F, G, H, I, J, K. And in here, if you use a queue and you push in B, C, D, the moment you pull out B and you process it, two things you have to do as part of processing. One of them is you add that particular name to whatever input array you have. And the second thing is you push its children to queues so that once everything goes out, all the children of this particular level is out, it would then start with the children of B, right? So that is what we're going to do with a breadth first search. Cool. Okay. Breadth first search. It's a classic BFS algorithm, and let's do it. Okay. Where am I going back here? Okay. Something is missing. This is missing. This is this. Don't need this. This is this. So yeah, it's basically deck of node, I think it's called. Yeah. You new array deck. So one of the things we can do is, we can give it a limit of how many elements it is. So as you can see here, it basically takes in the number of elements that you have. But the thing here is we are not very sure at like the maximum number of elements that you can have at a certain level. It's usually going to be 2 to the power that level minus 1. Yeah, because the first level is like, if I consider it to be 0, 2 to the power 0, or like 2 to the power level, right? But we don't know what level we're going to go for. So I'm just going to let it resize, which is not that big of a deal. But yeah, if you're using maybe a linked, something like linked list is a better option in here, but I'm just going to go with array deck. I'm just going with an array backed queue. Okay, cool. Where is my so the first thing you want to do is you offer this. Okay, and array dot pend this dot name because it's called add. Yeah. And then while the queue is not empty, you are going to pull this thing out. And again, here it says it forms an acyclic tree-like structure. That is why we don't have to do any visitor checks and all of that. We can simply just type it. Okay. Sorry. We can simply just type. Okay. Cool. So so the first thing we can the first thing we can do in here is, which means I don't have to do this here. I have to do this in here. Right. Because you push in the root or whichever node you're starting from, it actually has to be the root. So you start from there and you push in the name and array here. So next thing you do is for again, this cannot be null. Children cannot be null because we're explicitly giving it an initialize out here. So what you have to do is you have to say node children, which I don't like as you're calling it children actually. One thing maybe I can change here is we call something as neighbors, which might not be, I call something as neighbors, right? Maybe not. Yeah, children is not a correct term for a graph, but yeah, whatever. So node.children, if children not equal to null, you offer shy. Well, I make that wrong. Yeah, and that should be it. That should be the entire row. There's my I can probably, open my chat in here. Let's put we gotta mute the stuff. Let it play. So at least I know if it's working. Anyways, I hope, yeah, we still keep dropping frames here and there thanks to Airtel. Anyways, okay, so this is done, and we run the code. It's good. So this is good in here. I'm just gonna ask ChatGPT to summarize it. So yeah, we are good. So we did 3 problems. Yay! Cool, cool. So then you have river sizes. Okay. So you are given a 2-dimensional array matrix of potentially equal height and width. Contains only zeros and ones. Each zero represents land, and each one represents a part of the river. A river consists of any number of ones that are either horizontally or vertically adjacent, but not diagonally adjacent. Okay. The number of adjacent ones forms a river, determine its size. Note that a river can twist, in other words, doesn't have to be a straight vertical line. Makes sense, yeah. So it can also be a new and stuff like that. Write a function that returns an array of the sizes of the rivers represented in the input matrix. The sizes don't have to be in any particular order. Okay. I really don't want to. I really wish they let me copy it. Oh, awesome. I at least have it here. Maybe I should switch to Firefox. Only thing Google is beating Firefox is the DevTools. To be very honest, if you look at it, it has got huge, real powerful, things here. So yeah, I am not quite sure if my Firefox has that. But anyways, let me quickly see the stream health. Seems decent to me. Excellent connection and stuff like that. If you go to, yeah, okay. Oh, look at that! I got 2 likes. Thank you. Thank you. I hope you are enjoying the content. Well, I'm enjoying the process of this, and yeah, I love solving problems, and it's just a way of me documenting me solving problems and all that. Okay, cool. Moving on. So river sizes. What is a problem statement, right? So they are saying that 0, 1 is a river, and 0 is a land, and so this in here is a single river. This in here is a single river. This is again a single river. This is a single river. Yeah. This is another river. And this is another river. I hope I didn't miss anything out here. So it should be 1, 2, 2, 5. Is that the answer? Where's the answer? 2, 2, 2, 5. There are 2 2s. 1. Oh, my bad. Yeah. So 1, 2, 3, 4. 1, 2, 2, 2. And then this is 5. Yeah, that is correct. So this is another classic problem of connected components. And one of the easiest way we can do that is we start from here. So we can start from anywhere actually. So once we hit a water, which is 1, we try and mark everything adjacent to it, 4 corners, not corners, like horizontally and vertically adjacent to it. We try to mark them as visited. And once you mark them visited, you will know they say all good. So usually how I like to do this is I go row by and column by. Like I go by row and column. So I hit here and I hit 1. So I would go here and then I would, travel down, left, right, up, down, if it's possible. Up, down, up and left is not possible here. So you figure out you cannot do out of bounds and all that. But you go down and you mark this. So you try to go again and you do not. But the important thing here is that I shouldn't be able to go back. So I shouldn't be able to go back. One of the things we can do is we can keep another matrix saying visited. But that kind of brings in an extra space. Here, I want to see if you're actually expecting extra space, because generally in this kind of problems, you expect, yeah, you expect an extra space, which is with tighter rows or columns, right? But I'm going to do it with one space complexity. What I'm going to do is, as a matter of fact, given the constant of the problem, I know for a fact that the input is either 1 or 0. So here, I'm going to mutate this value to 2. So once I visit a particular cell or mark a particular cell visited, I'm going to change the value to 2. So 2 means it was a water before. It really doesn't matter what it means. Or like, it actually matters, my bad, sorry. What it means is that I have already visited that particular cell and I do not want to visit it. So I'm not going to visit anything which is 0 or 2. This way, I will be not iterating over, you know, um, like I wouldn't be going back to anything which I've already processed or the cell which I've already visited. The drawback here is just like the previous problem that we are mutating the input array, which is not a great thing. That if you give me an input and I mutate it, right? Etiquettes. Where is your etiquettes, buddy? You're gonna mutate. I give you something and I'm just gonna mutate it. That is not a great thing to do. So usually what I like to do is, it really doesn't cost much. I mean, again, it's a classic trade-off of time and space. I like to iterate over the array, the matrix again, and whichever values are, 2, I know it's gonna have to be 1 at some point, so I just change it back to 1. So I never actually mutated. Now there are certain problems with it. One of the problems is, what if the input is being used somewhere else by a different thread? But we are doing like a single threaded DSA problem with a single function given and not a full-fledged application, right? So I think it's fair enough. I just beat the system to do say that, hey, my space consumption is less, and I didn't mutate it already after the entire function is over. And if you're doing a multi-threaded environment, you have bigger problems. You're doing stuff without, sync and stuff, for your blocks and stuff, right? So that's a different problem. And the second thing here is that I think what is more of a valid discussion is that, hey, I have to iterate over the row and column more again. So isn't that a not time efficient thing? So people might come and say, oh, I already, I already iterate over rows and columns. So why can't I do it one more time? So if you do it, someone might come and say, oh, this is O of mn, 2 O of n. They are wrong. When you consider this, it's for huge numbers. We do not consider 2. I heard someone in an interview say, no, 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 no. So they're pretty much wrong. Okay. I don't know how to, like, say it without being rude, but you're straight up wrong. Your concept is wrong. You can say that, yes, it is technically gonna be more CPU cycles and it's gonna take more time. But when we are talking in terms of order complexity, it is not, because it's always taken into terms of big, huge inputs. This too doesn't matter. But in a real world application, this too might matter. This constant might matter and will probably matter, because you're iterating over a huge ass matrix again. So what is the solution for that? So there itself, I feel that you would benchmark and profile and feel and see that whether, because allocating an array also comes at a cost of time. You're allocating memory, right? So you are doing something like malloc and stuff like that if you're doing low level languages. So how would you get those memory, right? So yeah, I mean, we can also argue that if it's a huge matrix, you're gonna allocate a huge chunk of heap, and cleaning that up is gonna take some time. The garbage collector is gonna struggle with cleaning that up. It's gonna take some time. Someone might say, oh, you can just reclaim with one pointer and all that. I feel it can go in a very depth discussion, but for the sake of the problem statement, I am gonna take this approach, and I'm gonna claim that this is of one space complex. Okay, so I'm gonna claim that. That's all. Okay, cool. Let's get started. So what is the problem's name? Problem name is river sizes. Okay. Cool. So how do you do? Usually first thing I like to do is matrix length. and columns is this thing. This is huge of a problem. This thing matrix.length can fail if matrix is null. This thing can fail if length is 0, if the first element is uh, null. So these checks are missing. But again, taking into consideration that we are doing a DSA problem, it's usually within the constraints that these things will not fail. But in a production application, this is a no-no. Your PR is straight up rejected, saying add some null pointer checks. Yeah, cool. So now what do we do? So what we can do is for int row equals 0, row less than goes row plus plus, and this is column, this is column, this is column again. We have if matrix of row not equal to 1, straight up continue. If not, this is where we actually start our thing. This is where we actually start our thing. So the first thing is Java doesn't have anything called tuples or pairs. So how do you do it? One of the straight up things that, because I have to push the row and column both together, so I can of course create integer arrays and all of that. I feel that's stupid, and the syntax is really stupid whether I have to always do 0 and 1. So I can simply create a struct, a record, private record, and this column, call it cell, row int column. One of the things I can do here is that I can say, not public, let's just say it gives me a cell and next cell int direction, return new cell, row plus direction of 0, column plus direction of 1. Okay, and then I can also say well, boolean in range. Okay, so in rows, in columns, return row greater than equal to 0 and row less than rows, and column. Yeah, I cannot type. I mean, I cannot actually. Okay, so you have that. Next thing what you do want to do is, so for everything you do have to create a queue, and we can do that, and array, sorry, cell queue is new array tech. The problem here is for every iteration, whenever you find a new starting point, it will create a queue, which I do not want. I can reuse it. Specifically, I don't even have to call like queue.clear. I don't have to flush out the queue because I'm just gonna come to that. So queue offer new cell row column. Okay. Next thing what I want to do is matrix row and column should be equal to 2. This is it. Okay. And int size equals 0. Yeah, let's do 0. So now while queue is not empty, we keep on doing this. So you see queue would be flushed out by the end of the loop. So we should be good here. Int directions. So let's say you want to go left. So it is 0 minus 1, then 1 and 0, which is right. So if you have to go down, wait a second, 0 1, because right is column, yeah. If you want to go up, it's this, and for the other way around, down, it's this, right? So now cell is sorry, queue Okay, so now I'm gonna just do this thing. So I increment the size when I pull out something, so I don't have to keep a track of whether it was a first stuff or not. Okay, so this is it. The next thing I want to do here is I want to travel in directions, and I want to say cell next cell equals cell dot next direction. So if next cell dot in range rows and columns, and matrix of next cell dot row and next cell dot column is equal to 1. This is when we visit the next cell. You offer next cell. Yeah. So where do we stop? We stop somewhere around here. So once everything is done, what I have to do is arrays or something like that. Oh, I have to return something. So let's just say, oh, thank God, we have to return an integer. Sizes is new array list. Again, I'm not very sure how many things can be, so I'm not gonna, initiate anything. I'm gonna sizes dot add size. So let's call this river sizes, and this can be river size. River size, and that should be basically it. Yeah, that should basically be it. So let's go and see if we actually manage to go. Oops, there was a problem. Da, da, da. So for one thing I know for sure that I didn't do, which I mentioned I would be doing. So let me do that first. Row equals 0, row less than rows, row plus plus. It's column columns. If matrix of row column is 2, matrix of row column should be 1. Revert the flags. Basically flag. Okay, the question here is what is the issue? 0 minus 1 0 1 minus 1 0 1 0. Then you say row is this, okay, column is this, matrix, if it's not equal to 1, you say you want to continue to the next stuff. Then you say q offer, okay, new cell, row cell, matrix is this thing, okay, and you say row size this. Cool. In here, you try and get the next direction, which simply is like row plus direction of 0, column plus direction of 1. That is fine. Okay, so row is greater than 0 and row is less than this thing. Yeah, this also looks fine to me. So you try and iterate over the directions and you try and get the next cell. And if the next cell is in the range and the next cell row and column is 1, that is when you offer the next cell. Otherwise, you don't. So where exactly did this? And it happened pretty soon, right? It happened, it still took some time. My bad. Still took some time. My bad. Still took some time. My bad. Let's see where exactly this is. 1 second. Just a second. रुको, अभी इसको hello, hello. So, cool. Okay. So now we have to start debugging why exactly this thing went on an infinite loop, right? So yeah, next cell direction, if next cell in range, blah blah blah, all of that. If it's equal to 1, q of around that, okay. That is weird, to be honest, in my opinion. I don't see anything stupid, but let's see. So you have directions as this, you have row this, column this. If matrix is this thing in here, q dot of a new row and cell. And then you can say q is empty. Till it's empty, you pull out something to a reverse size. Okay. Yeah, we gotta actually start logging stuff and see where exactly it goes out of. You know, I'm guessing it goes here. Wait. Yeah, no, that's not it. So system out println cell. Wait, yeah, we can just do that, and hopefully that gives us a little bit more information. 00100. Okay, at some point, okay, keep going to and fro this thing. Hmm. The question here is, do you even exit out? That is very weird. 0 represents land and 1 represents water. Okay. So if it's not 1, it's wrapped up. So let's just also uh, system out print ln river sizes. Okay, so if you run the code in here, let's just see. Yeah, so you have 1, you have 1, which is again wrong, which is wrong right here. So you have 1 here, but this particular one, I'm a dumb guy. Matrix next cell, row next cell, column history. Who would mark it visited? I didn't never mark it visited, and that's the problem. That is the problem. Okay, yes, now it works fine. So we got the bug. It was a very small, subtle bug, and that happens. And that absolutely happens, right? So you have this. Let's submit. Sorry, and hopefully it passes. Hopefully it passes. Yeah, cool, cool. So this passes, I think, if I'm not wrong. Yeah. Let's go ahead and ask ChatGPT for the revision notes. BFS, GFS, blood filter count connected once, mark physical collected minutes. I feel there is also one other way to solve this, which is like, I don't remember DSU data structure, what is called? Disjoint set union. Yeah, DSU. So disjoint set union is basically trying to group together things into, trying to group together things into a single, trying to put things together in groups. So each individual groups is one set, and then you have a union of all those sets. Is how I figure out, how I understand. But it is also disjoint, so each individual sets are alone. So you have a forest of trees or a forest of graphs inside uh, uh, disjoint set union. So what you can say is, if you have 5 groups, you have 5 rivers, but then you can all individually go down the groups and see what are their sizes. Yeah, I have. This is also one of the things that I probably have to work on, which is like DSU. I have not done a lot of problem solving with DSU, but yeah, it's a pretty interesting data structure. Yes, cool. Let's move forward. So we're already streaming for almost, 92 minutes. I'll try to get 2 more problems done and take a break. And yeah, let's see. Maybe tomorrow I'll continue again. Um, let's see. Anyways, moving forward. Moving forward. Sorry. Youngest common ancestor, right? This is what it is. Youngest common ancestor. Still, we are on the, I think this is medium, if I'm not wrong. Oh, this is, yeah, medium level problems. So we have not hit the boogly board and all that. Boggle board. Anyways, cool. Youngest common ancestor. You are given 3 inputs. all of which are instances of, you're given three inputs, all of which are instances of ancestral tree, okay, that have an ancestor property pointing to their youngest ancestor. Ancestor is yeah, okay. The first input is the top ancestor in the ancestral tree. The only instance that doesn't have any ancestor points to null, and the two other inputs are descendants. Write a function that returns the youngest common ancestor to both the descendants. Note that a descendant is considered to be its own ancestor. Okay, so in a simple tree structure, a young ancestor to A and B is the youngest common ancestor to the nodes A and B is A. Okay. Okay, so you're basically given two nodes from the entire tree, and if like, yeah, it's basically like, okay, you have to find whoever is the youngest common parent here, right? I believe in this problem there is something called binary k shifting, binary k lifting, binary lifting, or something like that. Yeah, and I'm not aware of this algorithm, so this is a good, sorry, this is a good place to probably look at how this thing works. I know you try and go by two steps, something like that, or to like 2 to the power something step. Why and how it works is not sure. So how I'm gonna do it is, it's very simple. So it's A, B, C. Okay, let's extract it out again. Actually, okay. So how I'm going to do it here is, let's go back to the problem statement right here. So A, you have B, you have C, you have D, you have E, you have F, you have G, you have H, you have I in here. Yeah. So you're given the nodes E and I, right? So let's mark it E and I. And how I would like to do this problem is, I try to trace down the ancestors of the given nodes. So if I'm given I, so if you look carefully in here, it also has an ancestor, which means I can go up the tree. I do not have to come down from the root node. I can just go up the tree till I find the root node, or till, you know, the ancestor is not. So if I start from here, I, D, then B, then A. This is where you stop. And when you start from E, you have E, B, A. This is how you generated the list of parents. Now, I'm gonna keep on popping things out. So let's take this as a queue. So you put everything in a queue and then you start popping things out, right? Because I pushed it from here, so I'll pop things out from here. So now, since these two are not on the same size, so my offset is now messed up. So I need to figure that out first. So I would say, oh, this is I, this is 4, this is 3. So I would pop from here. So whichever is the largest one, I would pop from there. And if the, okay, so let's pop this. Good. So in here, we clearly see B is the parent right now. See that. So now the length is 3 and 3. When the length is equal, we look at the top. We peek and we see if they're same. If they're not the same, we pop both out. If they are the same, that is basically the, like, the youngest common thing. Sorry. So this is basically how I do it. But then here you would be using O of H as your yeah, O of H as your stack space, queue space, whatever, and you would be using two of those. I don't mention that constant doesn't matter, but here I'm explicitly calling out that I'll be using two of those. Right. I'll be using two of those. So that is kind of a problem. And if you look here, I'm pretty sure it requires of one space and of the depth, the height, time, and d is basically the height of the ancestral tree, or the maximum height at which your whichever node is present, right? But yeah, maybe tomorrow, maybe not today, it's already 11, so maybe tomorrow I'll start actually looking into what lowest common ancestor is and seeing how exactly to work with this um, algorithm. And this here is a actually good, again, sorry for flashbanging, but this here is actually a very good um, resource for, it says competitive programming. I'm not interested much into competitive programming, not for that, to be very honest, but it has a good amount of resources for your algorithms and data structure, and I believe that everybody needs to know those kind of stuff to actually solve good problems. Okay, so saying that, we'll keep this on the this thing, like on the backlog for now, and we'll try to finish off this with however we want to do it, right? So youngest common ancestor. So let's do this. I believe we have done good. Yeah. So in here, let's say I say private static uh, array deck deck of ancestral tree. I guess it could have been called node, but okay. Private static ancestral tree get ancestors. Okay. So ancestral tree, let's call it a node. So the question is, how do you do? How do deck ancestral tree view is this thing. Sorry. Now, let's just say, I mean, we can remove the node itself. So while node is not null, you pop. So let's be very clear. Sorry, offer last, if I'm not wrong. So let's be very specific because I remember we faced some problems. But yeah, let's do that. So you push this in. Okay, and then you say node equals node dot ancestor and return q, and let's just say ancestors. So in here, if descendant 1 is equal to top ancestor, if the pointers are the same, or descendant 2 is equal to the top ancestor, simply return the top ancestor as the youngest common. There is no other way anything else is gonna work out, right? No, there's no other way that anything else is gonna work out. Okay, cool. So now what happens here is, yeah, I have to call the function. So ancestors 1, I would say, is descendant 1, and this is 2 descendant. Okay, cool. So while ancestor 1 dot peak first not equal to ancestor 2 dot peak first, you're gonna have to keep on doing something. If ancestor 1 dot size is greater than ancestor 2 dot size, ancestor 1 dot hold first. Else if ancestor 1 dot size is less than ancestor 2 dot size, you have to Why did I even hold first? Else ancestor1 dot hold first and ancestor2 dot hold first. So here we are making an assumption that none of them are, like, it won't be null, is empty, and ancestor 2 dot is empty, and ancestor 1. So we are making this assumption, well, it's not empty. Yeah, we are making this assumption. If ancestor 1 is empty, we gotta throw some kind of legal exception, invalid input, unreachable for problem constraints. And in here, you can simply say dot, doesn't really matter, hold first. Exactly what we have to set, yeah. So that should be the problem. That should be the solution. I'm sorry. That should be the solution to the problem. We have to copy this also. You cannot be forgetting that. You cannot be forgetting that. So where are we? Yeah. This should do the trick, I believe. Okay, all good. We passed all the test cases. That is what we want. We're gonna submit. And also, green is what we like. Red is what we hate. We don't like our yellow, right? So green is the thing. If you got it, you got it. Okay. Okay, cool. Yes, I think we solved almost 5 problems, 5 easy problems. These are still marked as medium, but they're kind of easy problems in here, honestly. We can start with remove violence. I'm gonna just, how do I remove the, okay, anyways. So yeah, we can start with remove violence tomorrow, cycle and graph, minimum passes, blah, 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 and then, go towards more, um, um, difficult problems. So I think the gray ones are the hardest and the red ones are hard problems. But yeah, I think that's it for today. We already did a good amount of progress and learning. So tomorrow, the first thing I'm going to put a note in here. So first thing I'm going to, ask it to give me a note. I think it actually got very angry. Build ancestor chain, trim longer path, then move up until together common node. This can be done using binary lifting. Check the log. So we're gonna have to look into this now, because I believe, yeah, like I said, for each node will pre-compute its ancestors above him and its ancestors 2 nodes above his ancestor. Yeah, like I said, it's always 2 to the power of something. So again, I came across this algorithms, but I never really implemented by hand. So it means that I don't remember, because I don't remember shit ton of text for nothing, but nobody does. So I gotta implement it. And once I do implement it, I'm pretty sure if I understand how it's implemented and what's the maths behind it and why do you do it, oh, it actually gave you the entire book. So that should be it. And I should be more, better with this. I don't know how many times you're gonna have to do binary lifting in your actual development. So people keep talking about why leak code, why DSA, you'll never do it. And yeah, you'll never do binary lifting. That's true. But do I fucking care? No. I want to learn, and I'm going to learn. I don't care if it's used anywhere. As simple as that is what my theory is. Yes. Okay, cool. Thank you so much, whoever joined in, whoever tuned in. Thank you so much. I hope it was a good session. I hope it was a learning session. Even if you're watching offline, hope you learned something out of it. And yeah, I think it was a good one, though we solved pretty easy problems. Tomorrow I'll try to come online again and try solve more 5 of the problems. And after we are done tackling, so this is how I'm going to go about the data structures and problems now. I probably I don't know. I might solve the blind 75 again, just restart on it where I left off. But I felt it's much more fun for me to actually explore things which I haven't explored. So I didn't start with arrays. So, I keep on getting hits. Again, I keep saying that do some easy problems or do some medium problems, which gives you that dopamine hit saying, oh, I can do it. Awesome. That actually gives you the confidence. But you cannot always stick to. So graph is one of my not so strong areas, and I want to strengthen it. And yeah, this series is entirely gonna be on graphs. I'm gonna start with this thing. I don't know any other place where I can start, so I'm gonna start with this, where I'm gonna go with AlgoExpert, maybe then Lead Code Platform, and maybe then Lead Code Platform. I'm not directly going to Lead Code Platform because there are thousands of problems on graphs if you just filter, and it's very stupid to start solving every one of them. But yeah, let's see where we go from here. And one of the things I am also planning to do in here is I actually forgot the guy's name. So there's a Google engineer who has a really, really good DSA playlist. I of course probably cannot, run his videos on YouTube or my stream. I don't know what is the implications for that, but I can definitely, summarize the details, and I would actually say that okay, so maybe YouTube Bellman Ford algorithm video Google engineer. Can I find it? Wow. It gave me everything except that guy. It gave me everything except that guy. And I believe. Wait. This is true engineer. No. The 7-hour video course. Okay. Yeah. So I believe. Yes, William Fawcett. Got it. Thank you. William Fawcett algorithms. So I do recommend checking this channel out. His content is really good. And one of the playlists he has is, graphs. Where do you have graph? Okay, so you have graph theory, then you have network theory. So these two things together, I feel, has a lot of, information. Then he also works with bit trees and all that. So yeah, if you're really interested in these kind of stuff, and not just for interview purpose, which I really don't think should be genuinely interested in this. Here's a link in the chat, and William Fawcett for robotics. So do follow this guy. It's absolutely amazing playlist, and it's pretty good, pretty knowledgeable, pretty informative and educative. So yeah, that's pretty much it from my end. And then maybe also this thing you can actually look up. I'm just giving it this, but I suppose I can, yeah, I guess I can give this. So this, in my opinion, is also very informative, and it's not just for competitive programming. It's a pretty informative website where you have a couple of things, so you can go here, data structures. But more importantly, what I'm going to target here is algebras, geometry, and graphs. Combinatorics, numerical methods. Again, combinatorics is more about probability and stuff like that, fundamentals, things. So yeah, binomial coefficient, Caitlin numbers, factorial divisors. So it's pure maths, which is, again, it may not be helpful. You may never work on it, but I'm still gonna fucking do it. End of discussion. If you feel you shouldn't be, I mean, yeah, maybe you shouldn't be judged on it, but it cannot stop me from learning it. So Hungarian algorithm, this, that. Okay, there's a statement problem. Okay, why do you? Not quite sure. Anyways, there are n jobs and n workers. Each worker. Anyways, okay. So I'm not gonna get node sniped right now. Cool. Okay, thank you so much whoever joined in, and tomorrow again we'll try to come back live and keep continuing working on the graph theories and the graph problems. Till that time, Awesome. Thank you everybody for joining. So, thank you everybody for joining, and yeah, stay tuned. Do hit the subscribe button if you feel that the content is helpful. Like I more prefer to do journeys rather than just have videos, but I don't know, maybe I do plan to make shorter videos and stuff so that you know the algorithm has to be beaten. The algorithm has to be beaten. You have to play its game. But the second thing is that your um, yeah, if something is, I feel it needs to be made into a video, which I think a couple of things I have here and there. So I'll be making those videos, but it's more about the journey documentation. So it's more about the live stream and building a community to code for fun, and along the process learn something, right? So see you. Thank you everyone, and have a good day.